Hi class, this is the third lecture on acid-base equilibrium. And section, we're gonna go over chapter 14.3. We're gonna talk strengths and then do some calculations on acid-base equilibria. And that will be worksheets 16 and 17. So you might want to get those ready if you haven't already before you watch the lecture. You can work through them while I go through them at the end. On acid-base equilibria, it's the problem solving is similar to what we did previously in chapter 13 for general equilibria. And frequently we will set up an ice table to solve these problems. And so that's just a heads up. You can find, if you want more instruction on how to use ice tables to solve equilibria problems, especially acid-base equilibria, you can look at Khan Academy. He has lots of videos showing you how to solve these problems. So let's get started. As usual, I have a PowerPoint to show you. There's the PowerPoint. Oops. I thought it was at the beginning. Here we go. Still not the beginning. What's going on here? Beginning. Yeah. Okay. Okay, chapter 14.3, relative strengths of acids and bases. So our learning objectives for this section is to understand the factors affecting acid strength within molecules and be able to predict relative acid strengths. And so we can use a periodic table a bit to help us predict acid strengths, but also the molecular structure will help us decide acid strength also. Then later on in this section, we want to calculate acid concentration and pH for weak acids and weak bases. I think all the problems we're going to cover include weak acids, but they can be, the strategy for solving these problems can be applied to weak bases also. So first of all, when it comes to acid strength, you need to memorize these 6 strong acids and 6 strong bases. So there are many more weak acids and weak bases than there are strong acids. These are the common 6 strong acids and the 6 common strong bases. I think this table came right out of the book. And so the acids, we have perchloric acid. Another acid sometimes that's added is chloric acid, which is HClO3. So sometimes you'll see a list of 7 strong acids. And then hydrochloric, hydrobromic, hydroiodic, those are all halogen acids. Nitric acid and sulfuric acid. Strong bases contain hydroxide ion. So these are ionic substances of the alkali metal group and of the alkaline earth metal group. So strong bases contain hydroxide of the alkali metals and the alkaline earth metals. And the strong acids are these 6 or 7 acids. Now, in my face-to-face class, I would ask you to memorize these. But since we're at home, you can just print out this table, this list, and have it handy. You may be, it's important to recognize what acids and bases are the strong ones. So here's some acid dissociation comments. Let me back up a little bit. I think there's a slide later on that explains what's going on with a strong acid, but a strong acid is totally ionized when you add it to water. So when we talk about the concentration, you know, oftentimes in lab you'll have a bottle that says 1 molar HCl. Well, since HCl is a strong acid, that bottle of 1 molar HCl produces 1 molar hydronium ion. So if we want to calculate the pH, you just take the pH of 1 mole. That doesn't happen with weak acids because they don't ionize completely. Same with strong bases. If you add 5 grams of sodium hydroxide, that would equal a certain molar amount of sodium hydroxide. That turns into an equivalent molar amount of hydroxide ion when you put it in water. So here's a list of Kas. Now remember the equilibrium constant is the product over the reactant. And in the case of, let me just write it up here to remind you. So K, oops, what happened? Hold on. So K is product over reactant. And I'll just use a P for product instead of writing it all out, over reactant. And so in the case of a strong acid, I'll put strong over here. So a strong acid, K is, I'm going to use much, much greater than 1. I think in the case of HCl, it's something like 10 to the 6th, 10 to the 7th. So that's why we say all of the HCl turns into hydronium ion. In the case of a weak acid, K is always less than 1. So when K is greater than 1, the acid forms all product. When K is less than 1, mostly reactant is in solution. So not all of the substance ionizes. In your text, it talks about the percent ionization of weak acids. So we're not going to go into that very much, but we are going to use K a lot in doing calculations. So you can look at these Kas, and for an acid, we put a subscript A for Ka. The concentrations are in molarities. And so you always have to be sure you're using the molarity of the substance, the reactants and the products in these calculations. So in the case of hydrofluoric acid, we have a Ka of 3.5 times 10 to the minus 4. The larger the Ka, the stronger the acid. The smaller the Ka, the weaker the acid. These are pretty small numbers, 4.9 times 10 to the minus 10th. Hydrocyanuric acid is a very weak acid. There's some other acids. So 1.8 times 10 to the minus 4, 1.8 times 10 to the minus 5. These are all weak acids. The larger the Ka, as I said, the stronger the acid. So if you look at this table, the strongest acid in this table is hydrofluoric acid. The weakest acid looks to be maybe hydrocyanic acid. That has the smallest Ka. So there are other kinds of acids. There are these acids called polyprotic. These are monoprotic acids. They have one hydrogen, one proton comes off. The polyprotic acids have more than one hydrogen that comes off. In the case of sulfuric acid, H2SO4, the first proton that comes off to form hydronium ion is a strong acid proton. The second one is the weak acid. So you can see that H2SO4, Ka is really large. That's over here on the left. It's a strong acid. But HSO4 minus, the conjugate base of H2SO4, has a proton that can come off. And it is a weak acid. So HSO4 minus is a weak acid with a Ka of 1.2 times 10 to the minus 2. Here's phosphoric acid. The pKa's for the 3 protons for phosphoric acid. 7.5 times 10 to the minus 3 for the first one. But you can see as each proton comes off, it's harder, more difficult for the next proton to come off. And so the Ka's decrease. So we have the protic acids on the right, on the left side of this table, and the polyprotic acids on the right side. So here's a table that shows the relative strength of, and this scale is based on H3O plus. So H3O plus is a pretty strong acid. That's kind of in the middle of the scale. So the Ka of H3O plus is given as 1. Here's chlorous acid, hydrofluoric acid, and this is kind of the relative acid strength. So if the relative acid strength, the Ka, the relative acid strength would be the ratio of the acid strength of H3O plus over these others, or the others over that. So HClO2 is 1/100th as strong as H3O plus. This is 1/10,000th and so forth. So water we have down here is 1 times 10 to minus 14. So that's really the weaker acid. We said water has some acid properties in the presence of a base. If we look at bases, the strongest base in water is considered hydroxide ion, and then all these other bases are weaker than that. So that's the relative scale of relative base strengths. So here's another table showing the strength of acids. So at the top of this table on the left side are the acids and the right side are the bases. So the left side has the very top has the 6 strong acids that we talked about previously. And then hydroniumine. Now, hydroniumine is a strong acid, but it's not as strong as these other acids above it. So, and the reason why you know that is because if you put one of these acids in water, it forms hydronium ion. So remember, what makes an acid is losing a proton. And if you look at the equilibrium favors forming the hydronium ion rather than forming one of these other acids. So what I'm saying, if you have HCl, we'll write equilibrium here. And we're going to add water, H2O. Get H3O plus. That's what we've always written. Now we didn't write it with a double arrow before. And really with HCl, it's really favors the product side. So what this means is that HCl is a stronger acid than H3O plus because this is what forms. If H3O plus was a stronger acid than HCl, the reaction would go the other way, and we still have a lot of HCl. So all of these strong acids are stronger than H3O plus. It also means that the water, H2O, is a stronger base than Cl minus. So if Cl minus was a stronger base than H2O, it would take the hydrogen away from H3O plus and produce HCl. So the equilibrium always favors, and this always happens in acid-base equilibrium, it always favors the weaker acid and the weaker base. So in this case, this is the weaker acid. These are the weak. This is the weak side. This is the weak side. So in this case, in this equilibrium, the conjugate acid and the conjugate base are weaker than the acid and the base on this side. So this is the acid base side. And this is the stronger side in this equilibrium. That's not always the case, but in this particular case, when we add hydrochloric acid to water, the left side contains a stronger acid and base, and the right side contains a weaker acid and base. So the equilibrium always favors, this is important, that's an important point, equilibrium always favors the side with a weaker acid and base. We're going to see that over and over and over. So I'll point that out as we go through this discussion. In the base side, it's the same thing. So these are weak bases here. They're weaker than water. These are all stronger bases than water down here. So here's water. So all of these, let's see, where's water here? Here's water over here on the acid side. Okay. So all of these bases, nitrate, chloride, bromide, iodide, perchlorate, they're all weaker bases than water. So that matches up with what I said over in this equilibrium. Chloride is a weaker base than water. All these other things are stronger bases than water. That means if you put sulfate ion in water, it's going to take away a proton from water. So all these substances down here below water, when you put them in, when you put these salts in water, the solution becomes basic. So all these, when you put these in water, they all become basic. The strongest bases are down here. They're stronger than hydroxide ion. So they undergo complete base ionization. So sulfide, F oxide, these are strong bases that are stronger than hydroxide. So they don't even exist in water because they take a hydrogen away. Take a hydrogen away from hydroxide. They're stronger bases than hydroxide. Let's see, water, let's see. So here's the acidity of water. So everything above this is a stronger acid than water. Everything below is a weaker acid than water. So these substances do not go acid ionization. They don't lose a proton in water because water is a stronger acid. So if you put HS minus in water, HS minus takes a proton away. These are actually, well, HS minus is like a base. It's over here someplace with HS minus. There it is right there. It's a base, stronger base than water. Okay, so let's move on. And I'll talk about this relative acid-base strength as we go on. So one way you can look at the periodic table is you go along to the right side, and this was taken out of your book. It shows that ammonia is actually a weak base, but as you go further and further to the right, you increase acid strength. So as you look at the compounds, the elements that contain compounds with hydrogen, we have CH4. These are the nonmetals. CH4, NH3, H2O, HF. As we go to the right, we get stronger and stronger acids. SiH4, PH3, H2S. H2S is a weak acid. HCl, we get stronger acids as we go to the right. As you go down the periodic table in compounds, hydrogen-containing compounds with these elements, you form stronger acids. So HCl is a stronger acid than HF. And as you go down the 17th group, halogens, the acids keep getting stronger and stronger. So After HCl is HBr, that's stronger acid than HCl. After HBr is HI, that is a stronger acid as well. So this is just kind of a trend on acid strength of elements that contain hydrogen, elements with hydrogen. So these are binary acids, only two elements. There's a hydrogen element. Base strength. As you go, if you go all the way to the left, alkali metal hydride, that's an extremely strong base. Let's see, let me see what the next slide is. It might be, I want to talk more about acid strength. Oh yeah, here we go. So these are acids that contain more than one. They're not binary, they call them ternary. Ternary means acids that have three elements in them. So the three elements are something like nitrogen, oxygen, hydrogen in the top row, or sulfur, oxygen, hydrogen in the second row. There are also ternary acids that are halogens. So you can have an acid that, remember the perchloric acid, ClOH, ClO4, let's see, HClO4. That's what I'm trying to say, HClO4. So we have 4 oxygens around here. So there are lots of halogen ternary acids, HClO4, HClO3, HClO2, and HClO. Okay. Now, what happens with these ternary acids is you increase the number of oxygens, the bond between the H and the O gets weaker and weaker. Because these oxygens are electronegative, so they're pulling electrons away from this HO bond, making it weaker, so making it easier for this hydrogen to leave when it's put in water. And so in the case of nitric acid, we have 3 nitrogens attached to the, 3 oxygens attached to the nitrogen. That makes it a stronger acid than nitrous acid, where we only have 2 oxygens attached to the nitrogen. The same with sulfurous and sulfuric. Sulfuric has 4 oxygens attached to the sulfur, so it's a stronger acid than sulfurous, which only has 3. Chloric acid, or perchloric acid, is stronger than chloric acid, which has 3 oxygens attached. So chloric acid looks like this. It all has to do with this bond between the O and the H. As that bond gets weaker, the acid becomes stronger. And the more oxygens on that central atom, the weaker that OH bond. So that's the end of the discussion on acid strengths. So the book talks about it also, so you might get more information from the text if you need it. So let's go on to calculating the pH for strong acids and strong bases, and then also for the pH for a weak acid and a weak base. So the concentration of the strong acid is the concentration of the hydronium. Remember, pH is the concentration of the hydronium, not the acid. It's the hydronium that the acid produced. But for a strong acid, the concentration is equal to hydronium. So in this example, I used H2SO4. It's supposed to be a 2 there, not an S. To H2SO4. So we have 0.0394 molar H2SO4. Well, because it's a strong acid, because it's strong, the concentration of hydronium ion is also 0.0394. But that's only because it's strong. If it was a weak acid, it wouldn't be that. We'd have to use an ice table to calculate it, figure it out. But for a strong acid, the concentration of the acid is equal to the concentration of the hydronium ion. So the pH is minus the log of 0.394, which comes out to be 1.405. So I use the sig fig rule for logs. We have 3 sig figs in our concentration. So we add 3 decimal places in our pH. What's next? Anything else? It's the same calculation for strong bases. Because bases are ionic in their pure forms, which are solids, problems, calculations often begin with the mass and the volume quantities. And the molarity has to be calculated first. So don't forget that the calculations that we're using to calculate pH and pOH are molarities, moles per liter. So if you're not given moles per liter, you're going to have to calculate. In some problems, we're asked to calculate the pH after we've mixed an acid and a base together. Well, in that case, you're going to have to consider the increased volume, because when you increase the volume of a solution, the molarity goes down. So, or you have to at least recalculate the molarity. Okay, so don't forget that volume changes change the molarity, and sometimes that has to be recalculated when you do the problem. So I wanted to talk about another problem that I don't have there. But if you react a strong acid with a strong base, that's called a neutralization reaction. So if we have HCl, then we're going to talk about this is comes into titration before, but I wanted to mention it now. That's in the next couple of units. It's in this chapter, at the end of this chapter. But in this case, we have a strong acid and a strong base. And in fact, any acid-base reaction, you can say generically it produces water and salt if it's a hydroxide base. So we're going to get water and sodium chloride. Well, because it's a strong acid and a strong base, this reaction goes to completion. So whatever acid you have is going to neutralize whatever base you have, and vice versa. So if you put equal stoichiometric amounts, you don't have anything, you end up with a neutral solution. The pH would be 7. Because all you have is water. You wouldn't have anything left. So you'd calculate the pH of the solution based on the water. But if you don't have equal amounts, what you have to do is you have to figure out what the excess is. Okay, you might have a reaction, you add HCl to NaOH, you'll have extra NaOH. But you just subtract the moles of HCl from the moles of NaOH. The moles of NaOH left over, divided by the volume, is equal to the molarity of hydroxide ion. That's how you calculate the pH, based on the extra hydroxide ion in solution or based on the extra hydronium ion in solution. And I think we'll get into this kind of calculation when we talk about titrations at the end of this chapter. Well, I do have an example of what's the pH of a strong base. So what is the pH of 300 ml solution that contains 1.345 grams of KOH? So to calculate, we have to calculate the molarity first. So we have 1.345 grams divided by 56.11 grams per mole, divided by, let's see, this gives us our molarity, a number of moles, I should say. This gives us our moles. We divide moles by liters to get molarity. So we have 0.799 molar. Our pOH is minus the log of 0.799, which is 1.097. This is our pOH, remember? So we're going to take 14 minus the pOH, and it gives us our pH of 12.903, which, since we're using KOH, that makes sense. This is a basic pH. It's above 7. So always when you're doing these problems, think, does it make sense? Would you predict that solution would be acidic or basic? And then when you do your calculation, that's how it should turn out. That's really a rough estimate of whether your calculation was done properly or not. A reminder, strong acids and bases essentially react completely with water to form hydronium ion or hydroxide ion. Their equilibrium is all on the product side. So let's look at calculating the pH for a weak acid and a weak base. So weak acids and bases are in equilibrium with hydronium ion and hydroxide ion. Well, the acid is in equilibrium with the hydronium ion, and the base is in equilibrium with the hydroxide ion, according to the equilibrium constant. So in the case of a weak acid and weak base, the K, we use a Ka for the acid. It's going to be less than 1. And for the base, the Kb is going to be less than 1. Thus, the equilibrium lies on the reactant side. So in your book, they have several examples of how to do these problems. I would look at these. So as examples 14.9 through 14.14, it's a really good sampling of different types of problems that you will encounter with this, this topic. So we're going to do a couple, but we're not going to exhaust all the possibilities. I'm going to show you a few examples on the 2 worksheets we're going to do, worksheet 16 and 17, that exemplify the kind of problems you'll find with weak acids. I'm not going to do weak bases, but the weak bases are the same. The difference when you do a weak base problem, if you're asked to calculate the pH, is that when you solve a weak base problem, you can end up with a hydroxide ion concentration. You have to convert that to POH and then subtract that from 14 to get pH. So what is the pH of a 0.1 molar solution of acetic acid? Okay, acetic acid, I'm going to abbreviate HA maybe. I'm not sure. Sometimes acetic acid is abbreviated HOAC. Or sometimes HA, maybe HAC for acetic acid. So we don't have to write all the carbons, hydrogens, and oxygens in it. So let's look. So the first thing you want to do is you set up your ice table, because this is a weak acid. So here's an example of the ice table here. So we have, I always like to write the equilibrium that's going on in front of the ice table, and this should have an arrow going both ways. So we're starting with 0.1 molar acetic acid. That means initially we put 0.1 molar in the initial concentration. HAC is 0.1. But we have 0 for the hydronium ion and 0 for the acetate anion, conjugate base. So here's the acid, here's the conjugate base for acetic acid. So the change is going to be, because we don't have any product, you always have to think about which way is this equilibrium going to go. Because there's no product, it's got to go to product. So when it goes to product, we're going to lose an X amount of reactant, H, which is the acetic acid in this case. We're going to lose an X amount of acetic acid, and we're going to form an X amount of hydronium ion and acetate ion. Now, this question is about pH. So that's really has to do, pH has to do with the hydronium ion. But we can also be asked to calculate the concentration of acetate ion, but really because we're talking about pH, this is about acids and bases. pH is what is commonly asked for. So you insert the equilibrium concentration in the equilibrium expression. Whoops, Let me see. Something went wrong here. Here we go. I don't know what I did, but let's continue from the current slide. There we go. Okay. All right, so our equilibrium concentrations that are going to be 0.1 minus X for acetic acid, X for hydronium ion concentration, and X for acetate ion. So it says insert the equilibrium concentrations into the equilibrium expression. Well, if we do this and solve for, we'd have X squared over 0.1 minus X equals 1.8 times 10 to the minus 5. But because, here's a trick we're going to use in these kinds of calculations. If the Ka, if the equilibrium constant is really small, and the book talks about book says that if, I think if the concentration that we start with, the 0.1 is less than, or is greater than 1,000 times less than this, so you take the 0.1 divided by 1.8 times 10 to the fifth, and it's greater than 1,000, you can use this. But in most of these, in all of these problems, we use this. If it's 1.8 times 10 to the minus 5 or greater, and this is like 0.1 or greater, 0.01, you can use this trick that I'm going to do. The trick is called the small x estimation. And the small x means that the x value, this increment of HAC, of acetic acid, this amount of acetic acid that we're going to lose is way smaller than 0.1 molar. So we can neglect it in our calculation. So in our equilibrium calculation, we're going to just say this is insignificant, the x, and we're just going to put 0.1 in our equilibrium expression. So in that case, we have x times x, because we have, these are products, it's x squared over 0.1 minus x. Oh, here we go. Then we have our small x approximation. So we get x squared divided by 0.1. So this makes it pretty simple. We can take the square root of this right side now. So x is going to equal 1.8 times 10 to the negative 5 divided by 0.1, which becomes 1.8 times 10 to the negative 6. We'll take the square root. We find that x is equal to 1.3 times 10 to the negative 3. So let's take the log of that, because x remembers the hydronium ion concentration. We take the log of that, we end up with pH of 2.9. So that's the pH of a 0.1 molar acetic acid solution. I've got it. So that's, let me write that down. I want to write that down, what I was trying to do. So the pH, we said, equals 2.9. Now the reason why I want to write this down is because we're going to do lots more problems on the worksheets that have to do with 0.1 molar acetic acid solution. And I want to remember this. I'm going to actually write it on a worksheet someplace. I do have it written down, so that's okay. All right, so if you have any questions about this PowerPoint, be sure to join me in my office hours on Monday, and I'll answer any questions you might have. So let's go on. I'm going to end my screen share. I'm going to turn on my camera. There it goes. We're going to look at worksheet 16 and 17. So 16 actually is a worksheet deriving the equilibrium expressions for weak acids and weak bases. And then also the acid and the conjugate base. And so the first question is, I'm not going to read the top part, you can do that. But the first question, the first problem says, write the form of the acid dissociation expression for hydrocyanic acid in water. So the Ka for this is pretty straightforward. It's a concentration, it's a hydronium ion concentration, which is the product in this equilibrium expression, times cyanide divided by HCN. We don't include water because it's a liquid, okay? Remember, we don't include liquids or solids. So H3O plus times HCN over, H3O plus times CN minus divided by HCN. Those are molar concentrations. If the equilibrium was going the other way, then we would invert that. Remember how we did manipulations of the equilibrium constants previously. Okay, the second question. Write the form of the base ionization expression for the cyanide ions. The cyanide is a weak base. So Kb, here's the form, generic form for the weak base. So the Kb in this case is going to be HCN, the molar concentration of HCN times the molar concentration of hydroxide divided by molar concentration of cyanide. That's our expression there. So that's pretty straightforward. Question 3, it says, note that in the preceding two chemical reactions, both the acid in the first reaction and the conjugate base in the second reaction react with water. That's what acids and bases do. We said we're talking about acids and bases in water. Sum these two chemical equations and determine the value of the equilibrium constant. Using Ka, 6.3 times 10 to the minus 10, and Kb for CN minus 1.6 times 10 to the minus 5. So I've written the solution. So to do that, what we're going to do is it says sum these two chemical equations. So when you sum the two chemical equations, you multiply the equilibrium constants. If you remember that from chapter 13. And so I've summed the two equations. So if you look at the sum of the two equations, HCN on the first equation is on the reactant side, but HCN is the product on the second equation, so they cancel. Similarly, CN minus is the product on the first reaction, and CN minus is reactant on the second reaction, so those cancel. So we'll add those together, and what we end up with is two H2Os in equilibrium with H3O plus and OH minus. Well, this is the Kw. This would produce Kw. That we talked about previously. We were learning about tackling pHs and POHs. Remember Kw, what's Kw equal to? Kw is 1 times 10 to the minus 14th. I can just leave off the 1. We'll just say Kw is 10 to the minus 14th. Well, let's see what happens here. So our Ka is 6.3 times 10 to the minus 10th. And our Kb is 1.6 times 10 to the minus 5, right here. Oops. Right here. So we're going to multiply them together. We're going to get a combined K. K is equal to Ka times Kb when we add the two reactions. So we're going to have 6.3 times 10 to the minus 16 times 1.6 times 10 to the minus 5. When we do that, we get 9.6 times 10 to the minus 15. Well, that's pretty close to 1 times 10 to the minus 14. So what's important to know, for an acid and its conjugate base, if you multiply their equilibrium constants together, you get Kw. So that's an important equation. If you know one but not the other, we always know what Kw is. So if you know Kw is Ka times Kb, if you know Ka, you can calculate Kb. If you know Kb, you can calculate Ka. In some problems, you have to do that. Some problems you'll be given Kb, but you need to know Ka. Well, they're related through the Kw, the ion product constant for water. So I think that's all for our worksheet 16. In our subsequent worksheets, we're not going to be using that relationship Kw equals Ka times Kb, but that's an important thing to remember. Okay, so this is called the common ion effect. These problems are, we've titled this worksheet the common ion effect. And what we're going to look at, we're going to look at weak acid-base equilibria, really weak acid equilibria. So I'm going to write down the generic. I'm going to look at this equilibria. HA plus water, and water is in equilibrium with H3O plus A minus conjugate base. Okay, so when we talk about this common ion effect, that means the ions in this expression are on the product side. So if we add a little extra hydronium ion, what's that going to do? So if we have an equilibrium with HA and we add some product, well, what we learned from Le Chatelet's principle, that the reaction is going to go to the left. So if we add product, if we add one of these ions, it's going to shift to the left, and the other ion will go lower, and the reactant will increase. So if we add a little acid to this equilibrium, that means the anion is going to go down. Okay, so the acid is going to go up, so it'll be a little stronger, but this will definitely go down, and this will go up. On the other hand, if we add the anion, if we add conjugate base to this equilibrium, the hydronium ion is going to go down. Well, we express that as a change in pH. So if the hydronium ion goes down, remember pH is opposite to acid concentration. So if acid concentration decreases, pH will increase. So that's what these problems are about, is exploring this equilibrium and adding one of these ions. And so the first problem is calculate the pH of a 0.1 molar solution of acetic acid. Well, that's what I did in the PowerPoint. So I'm not going to do that again. I just say see the PowerPoint. Here's the equilibrium reaction shown here. And I just took a few values off that PowerPoint that we want to refer to. One was the hydronium ion concentration was 1.34 times 10 to the minus 3. Remember, this is the X. That was also, that's this side. That was also the acetate ion concentration. So they were both 1.34 times 10 to the negative 3 molar. The pH was 2.87. So I'm going to be referring back to these values as we go through these other calculations. So question 2, I'm going to scoot down here. It says calculate the pH. What I'm going to do is I'm going to Probably doesn't make any difference. I think you can see this full screen. I'm going to make this a little bigger. Calculate the pH of a solution that is 0.1 molar in acetic acid and 0.1 molar in sodium acetate. So that's how we add acetate. You can't add acetate ion by itself. You have to add it as a compound, as a salt. So sodium acetate is what we use. Could be potassium acetate, any alkali metal or alkaline earth metal acetate would work. But sodium acetate is very common. So we have our Ka is 1.8 times 10 negative 5. That's equal to, we're going to write our equilibrium expression, hydronium ion times acetate ion over acetic acid. We've seen that before. So number one, we're going to make our ice table. So that's what I said before. That's how we do our problem. So we started with 0.1 molar acetic acid. We have, initially we say there's no hydronium ion, but we have 0.1 molar acetate ion. So we start with 0.1 of this and 0.1 of that. We don't have any acid, so that means equilibrium has to shift to the right. It's going to have to go to the right because we don't have any acid at the beginning. Since it's going to go to the right, it means we're going to lose some acetic acid to produce some hydronium ion. We're also going to produce a little bit of acetate ion. So at equilibrium, we have 0.1 molar acetic acid minus X amount of hydronium ion, and 0.1 molar plus X acetate ion. So we're going to use that small x approximation. So we're going to neglect these x's. So we'll say in our equilibrium expression, we're going to have x times 0.1, x times 0.1 divided by 0.1. So our equilibrium expression looks like this. Remember, we'd use the small x approximation. So in our small x approximation, I use a different color pen here. I'm not going to use that. Oop, no, this didn't work that great. Anyway, we neglect this x, those x's. Okay, those are the ones we do away with. So we end up with 1.8 times 10 to the minus 5 equals x times 0.1 over 0.1. Well, the 0.1's cancel. So x is going to equal 1.8 times 10 to the minus 5. That's our hydronium ion concentration. So our pH is going to be 4.74. Well, a couple things. Because we added this common ion, that means our equilibrium is going to have to shift to reactant. We're going to have less hydronium ion than if we didn't have the common ion. So let's compare our concentration. So we have 1.8 times 10 to the minus 5 in a solution with added acetate. In the solution without added acetate, we have 1.34 times 10 to the negative 3. So that's a lot more hydronium ion concentration. Reflected in the pH, this pH is 2.87 without acetate ion. This pH is 4.74 with acetate ion. So less hydronium ion is produced, which is what we would predict from what we know about chemical equilibrium. Okay, let's go to the next page. In this case, it says, consider what happens to the pH. I'm going to cover up all this stuff. Consider what happens to the pH of the above solutions when a strong acid is added. So what is the pH of the solution prepared as in 1 above, but also has a 0.01 molar HCl added? Use the initial equilibriums is what it says for your starting point. So what we're assuming is we're not going to change any of the volume. Remember I said sometimes if they give you the volumes and the volume changes, then you have to refigure the molar concentrations. But in this case, we're going to assume that there's been no change in volume, that we have a solution that contains 0.1 molar acetic acid and 0.01 molar HCl. So here's our equilibrium concentration. We set up our ice table. Here's our ice table. So we have 0.1 molar acetic acid, 0.01 molar hydronium ion, because HCl is a strong acid. So 0.01 molar HCl produces 0.01 molar hydronium ion. Talked about that previously. Acetate ion is 0 initially. Since acetate ion is 0, the equilibrium is going to shift to product. So the equilibrium is going to go this way, with a big arrow that way. So we subtract an incremental amount of acetic acid. It's going to produce a little bit of acid. And it's going to produce a little bit of acetate ion. Now, this is a case where, remember previously in the second problem, we started with 0.1 molar acetic acid and some acetate, and we saw that the hydronium ion formation was suppressed. It was lowered because of that. This time, we're starting with 0.1 molar acetate ion, and we're adding acid to it. So we'd expect that the acetate, so we have acetic acid, hydronium ion in this solution. Acetate should be suppressed, should be lower than previously. Let's see if that happens. So we end up with 0.1 molar acetic acid minus X, 0.01 molar hydronium ion plus X, minus X plus X, and plus X for acetate ion. So again, we're going to use our small x approximation, so we'll neglect the x's. Take these x's out. So when we plug in what's left into our equilibrium expression, we get 0.01 times x. The only x left over is the acetate ion divided by 0.1. It's going to equal 1.8 times 10 to the negative 5. We arrange to solve for x. It looks like this. So x is going to equal 1.8 times 10 negative 5 times 0.1 over 0.01. So we get 1.8 times negative 4 for acetate ion. So if we remember previously our acetate ion on the first page, I'll have this up here for reference. Originally, the acetate ion was 1.34 times 10 to the negative 3. So it went from 1.34 times 10 to the negative 3 to 1.8 times 10 to the negative 4. So to calculate the pH is really 0.01 plus this small amount, which might be 0.01, 102. And we take the log of that, and you get pH is 1.99. So the pH went a little bit lower, not too much. We could do the same approximately. We could say the pH is going to be minus the log of 1, which would be 2. Now, if you plug in these values, if we correct for this x, we neglected the x in the calculation because we said it's insignificant, and it's pretty insignificant. But if we plug this in, we don't exactly get back 1.8 times 10 negative 5. So if we include x here, and x here, and and then put it in the equilibrium expression to do our check. Well, we get about 1.95 or something like that. We don't get 1.8. So another way to do these problems, if you wanted to do them without solving the quadratic, we could solve it for the quadratic, get the exact value for x. But to solve it without the quadratic, there's a thing called successive approximations. So if we plug in our value of x here, 0.1 minus x, 0.01 plus x, and solve our Ka, it comes out a little bit higher than 1.8. So that means there's a little bit too much product. It means that x is a little bit too big. So we do a thing called successive approximations. You lower the x a little bit. So instead of x equal to 1.8 times 10 to the minus 4, we're going to lower it to 1.75 times 10 to the minus 4. And actually, when you do that, and you plug x back into your equations, into your equilibrium, you get pretty close to 1.8 times 10 to the negative 5. So our actual x is a little bit less, but 1.75 times 10 to the minus 4, if you round it up, you know, to 2 sig figs, that's all. We only have 1 sig fig here. So our approximation is pretty good. But there's another way to solve these. And with a computer, it's really easy to zero in on the exact concentration of x because it can approximate this. It can do a loop calculation. And even with a programmable calculator, you could do that. So that's another way to solve these. It's called the method of successive approximation. And you can do that instead of using a quadratic. In fact, if you have a problem that you can't use a quadratic, where you have x to the cube or something, that's how you would do it. Okay, the last problem. What is the pH of the solution prepared as in 2 above? So what was 2? Let me go back to 2. Here's 2. 2. Calculate the pH that has 0.1 molar acetic acid and 0.1 molar acetate ion. So we have 0.1 molar, we have 0.1 molar acetic acid, I'll put HAC, and we have 0.1 molar sodium acetate. And we're going to add 0.01 molar HCl to that. Use the initial, not the equilibrium concentrations for your starting point. Okay, so HCl is a strong acid. So when you add a strong acid, so let's look at our equilibrium again. Here's our equilibrium. Now here's where you have to consider the chemistry that's going on. So our equilibrium is HAC plus water. It's an equilibrium with H3O plus AC minus. So we said in this equilibrium, the equilibrium always lies, remember previously in the PowerPoint, I said that when we were talking about acid and base strengths, we said the equilibrium lies on the side of the weak acid and the weak base. So the side of the weak acid and the weak base is over here. That's where the equilibrium lies. So if we add a strong acid to this equilibrium, and we have a base present, this is the strong acid, strong base side. If you have base present, they're going to react together. So if we add a strong acid and we have a strong base, so this is the strong acid, strong base side, the first thing that's going to happen, it's going to go straight to the react, it's going to form reactant. So you have to consider that. Now, when we add acid before, there wasn't any acetate ion. So the acid just stayed there in problem 3. But if we have acetate ion present, that acid is going to react, the HCl that we add is going to react with the acetate. So if we make our ice table, when we start off, we have 0.1 molar acetic acid, 0.01 molar HCl, hydronium, and 0.1 molar acetate. But I just said these are going to react because you have a strong acid and a strong base in this equilibrium. They're going to react. So the 0.1 molar goes away. So we're going to lose minus 0.1 here. We're going to lose minus 0.1 here. Now, if we knew the quantities, if we knew the volumes, we'd have to figure out the molar concentration. So we know what the molar amounts are. But we'll say the volumes haven't changed. And so we can just subtract 0.01 from here and 0.01 from that. So we're going to add 0.01 here. Like I said, if you knew the volumes and you knew the concentrations, you would have to figure out this minus here is really the moles of this. However many moles of acid we have, we're going to react with the same number of moles of acetate and add to that number of moles of acetic acid. So we have to recalculate these equilibrium concentrations, but we don't know that here because we haven't been given volumes in this problem. So we're figuring all this is happening and the volumes are not changing. So then we have a new initial concentration situation. I call that I prime. This is a modified table here. This is I prime. This is a big ice table. It's I, C1, I prime, C2. So we have a new initial concentration. So we have 0.11 molar acetic acid, 0 H3O plus hydronium ion, and 0.09 molar acetate ion. Now they've got to change because you don't have any acid here. So we've got to produce some acid. So it's going to be minus X plus X plus X. So we end up with 0.11 minus X in equilibrium. This is what's going to go into our equilibrium expression, 0.11 minus X. X for hydronium ion and 0.09 plus X for acetate ion. So let's plug those in our equilibrium constant. So we have K equals 1.8 times 10 to the negative 5 times equals X times 0.09 divided by 0.11. So X is going to equal, here we go, X is equal to 1.8 times 10 to the negative 5 times 0.11 divided by 0.09. Remember, X is a hydronium ion, so we solve for that. X is equal to 2.2 times 10 to the negative 5. That's hydronium ion. And the pH is 4.66. So if you notice, the pH didn't change much. So the pH, when we did this before, problem 2, was problem 2. The pH was 4.74. But because that added acid reacted with acetate, it didn't change the pH much. It just went from 4.74 to 4.66. You look in the previous problem, let's look up here. Here's where we added some acid. The pH went to 1.99 and moved a lot more. So before, see, I've got it over here, all right here. Before the pH was 2.87, when we just had 0.1 molar acetic acid, and when we added 0.01 molar HCl, it dropped to 1.99, almost the whole pH unit. When we have sodium acetate in there, oops, let's see, when we have sodium acetate in there, go like this. Here we go. Okay, I see. There we go. I'm looking for the wrong thing here. Here we go. So with sodium acetate, the pH was 4.74. And then when we add HCl, it only changes to 4.66. It hardly changed at all. Well, this is the result because when we have an acid here, this is a preview now. When we have an acid and its conjugate base, both present in the solution, it's called a buffer. What happens to a buffer? When you add an acid or a base to a buffer, the pH does not change much. And that's the end of this. And guess what? The next lecture that we're going to have will be on buffers. So let me get a and I'm gonna go back to the camera. So that's the end of our lecture on weak acids and weak bases. And the next lecture will be on buffers, which is section 14.6. And that's all for now. So take care. See you next time.